Okay, Assalamualaikum everyone. Joule's law ni is about energy. So from this energy, so basically, so energy is come from when we move electron, okay, ataupun charge lah. So charge could be electron or proton. So charge from one point to another. Okay, so let's say from this point. So let's say we consider positive charge. So this is our first point. So we move the charge to the second point. Okay. So on this particular case, so basically the charge has been moved. It's about delta L lah. Okay, so berapa distance dia. So that's why in the end, so we will have the delta W. So delta W is the change of energy is equal to Fe. So Fe is the force that bring the charge move, okay, ataupun force yang menyebabkan apa nama tu charge ni bergerak daripada point 1 ke point 2 lah. Alright, so multiply by delta L. So delta L ni how much the charge has been moved. Okay, so yang gini on the respective of electron lah. So that's why we have Fe. So plus vector of okay FH delta L lah. So delta L so associate with H. So this one is associated with electron. So this one is whole motion lah. So in the end, so from this equation, so kalau you refer to the derivation, so in the end we will have power equation. So P is equal to integration of V E dot vector of J dot dV. So yang ni, this is equation that reflect our Joule's law lah. Yang paling penting ni bila kita belajar electric circuit, so in the end of the day, so basically from Joule's law ni, so we convert P is equal to I squared R lah, I squared R or VI or V squared divided by R. So so that's the concept lah basically. But the thing is, the topic is want to show you, so how can we get from energy, so yang ini energy lah, okay, energy change when we move one charge from one point to another. So daripada perubahan energi ni, so how can we derive the power equation? So that's soalan. Okay, so dalam soalan ni, soalan exercise ni, so let's say we have a 50 meter long, 50 meter long copper wire. As a circular cross-sectional section with radius R is equal to 2 cm. So the radius equal to 2 cm lah. So give that the conductivity of the copper. So we have sigma copper given in this question is equal to 5.8 times 10 power of 7 Siemens per meter. So first we need to determine the resistance of the copper. So R is equal to L divided by sigma A. So L ni is associated with the length of the copper lah. So it's equal to 50 meter. So divided by sigma. Sigma is conductivity. 5.8 times 10 power of 7. So multiply by the cross-sectional area A. So dia bagi kita radius kat sini. So pi R kuasa 2. So pi. So the radius is equal to cm 0.02 the power of 2 lah. So this one we will have how many resistor lah for this particular wire. So for the B, they ask us to find what is the power distribution in the wire is dissipated in the wire if the voltage across its length is 1.5 millivolt. So V is equal to 1.5 millivolt. Alright, so P is equal to V squared divided by R. So V squared 1.5 milli. Okay, kuasa 2 bahagi dengan resistor ni kita dapat lah tadi. So kita dapat lah mendapat sama dengan berapa watt. So dia punya contoh pun lebih kurang gitulah. So repeat the question, repeat the part B exercise by you applying Okay, so yang ini is a straightforward solution. Okay, if we are using the circuit theory equation. So the other next exercise tu dia minta kita gunakan persamaan S to solve repeat the part B. So by using P is equal to volume integration sigma the vector of E power 2 dV. Okay. So yang ini the technique that we use here is from circuit analysis technique. Okay. Let's say we want to solve this one. Okay, this exercise by using the fit technique. Okay, so we need to derive. We need to use this equation lah. Okay, but then we need to find first. So what is the vector of E? Okay, so what is the vector of E? So we are given in this question. So we have V is equal to 1.5 millivolt. All right. So from this value of V, in order to find E, so we have one expression. We have expression of E. E is equal to minus del dot V. Okay. Kalau kita di next page. So we have E is equal to minus del dot V. Alright. So in order to solve this, okay, so since in this case we are deal with the cylindrical conductor. Apa cylindrical shape of conductor kan? So kita punya conductor is in cylindrical shape. Okay, so that's why in order to solve this one, so we need to using the cylindrical coordinate system equation. Okay, so kalau 50 meter long is equal to 1.5 millivolt. Alright, so if we want to find the expression for each meter, so we will have 1.5 millivolt, so divided by 50 lah. So, kalau ni so let's see whether we get the same result or not. So 1.5 milli to divided by 50, then we will have is equal to the 3 microvolt. Alright, so the 3 microvolt per meter per length. So at the same time, so we will have the expression for V is equal to 30 milli, so divide multiply by the length. So let's say we assume that our length is in a Z direction. Okay, because of normally when we have cylindrical conductor, okay, like this shape. So basically, we can have the coordinate in terms of radius, angle, and as well as Z. Okay. So and most of the time, so basically, the function of the length is in a Z direction lah. So if we put back into our expression as, so we will have minus r cap dr plus phi cap 1 over r plus z cap dz. Okay, so I weigh with 30 micro z. Okay, so if you solve this one, then we will have on the dr factor, of course we will get a 0. So in this case, so of course we get the 0 as well because we didn't have any function of phi. So it left us with this one. So we will have our E is equal to Z cap. So dz. So this one is supposed to d phi dz. So dz 30 micro z. So pun doesn't make sense juga lah actually. So we have negative. So, kalau kita depreciate kan habis lah kan. So akan ada 30 micro only lah. 30 micro only. Okay, tak apa. Kita tengok dulu So volt per meter. Okay, so we have the vector of E is equal to minus minus apa tadi? 30 micro. If we want to apply the equation that we have just now, so we have P is equal to volume integration sigma dot vector of E power of 2 dV. Okay, if we consider we have one cylindrical, so we will have a triple integration lah. So we have first is R is between 0 until 0.02. So we have phi from 0 until 2 pi, and we will have the Z is from 0 until 50. Alright, so the sigma is given in the question is 5.8 times 10 power of 7, okay, Siemens per meter. 5.8, okay, so multiply by the E squared, okay, so in this case, so we will have minus Z cap 30 micro, okay, multiply by minus Z cap 30 micro, okay, then dV will be R dr d5 dz. Okay, if you solve this one, then we will have, so kalau dot product ni, then kita akan dapat satu lah. Alright, so minus z is positive z squared, so we get 1. Alright, so we will have 30 micro multiplied by 5.8 times 10 power of 7. Okay, and by solving all this one, so we will have R will be R squared divided by 2 is from 0 until 0.02. Okay, so dot with, we didn't have any phi, so phi from 0 until 2 pi, and the Z is from 0 until 50. Betul-betul, basically this is the way how can we solve it. Betul lah. So basically saya tertinggal ni, satu ni. So basically, if you solve this one, so z cap, then we will have 1, right? So kat sini supposed to ada the power of 2. So if you solve this one, so kalau saya selesaikan dapat 3.3 milliwatt. Okay, milliwatt. So the answer is the same as, so basically the answer is given in this book lah, is equal to 3.3 milliwatt. Alright, so I explain back lah. Kita tengok balik daripada awal lah. Okay, so we have 50 meter of a copper wire. So the radius for the copper wire is 2 centimeter. Alright, and the conductivity of the copper is equal to 5.8 times 10 power of 7 Siemens per meter. So this is the information that given in this question. Alright, so first the question asks us to find the resistance of the copper wire. So basically we can find by using general expression. So we have R is equal to L divided by sigma A. Right, so sigma is conductivity of the copper lah. So the A is represent the area, cross-sectional area of the copper. So if I draw this copper wire, so we will have arrangement like this one lah. So we have the length is equal to 50 meter. Okay, and the radius here is equal to 2m. Okay, since in a normal conductor, alright, so basically the current will be flow in this direction. So that's why, so the R here will be the represent the length of the copper wire, and the cross-sectional area is the area that perpendicular to the current direction. So in this case, so the area should be in this surface lah. Okay, this surface. So L is equal to 50 meter. So sigma is 5.8 times 10 power of 7. So multiply by the area. So this is the area lah. So pi r squared. So pi multiplied by radius. So radius, so please remember guys, you need to convert the unit to the SI unit. Alright. And then, so we can calculate. So kalau kita refer jawapan ni sama dengan 6.9 times 10 power of negative 4. Negative 4. Right. So then the question asks us, so let's say we put or we inject this copper wire with a voltage equal to 1.5 millivolt, then we need to find the power. So if we use the power equation, okay, so this is based on what we have been learned during circuit analysis. So we will have P is equal to V squared divided by R. So V squared is equal to 1.5 milli with the power of 2. So divided by R. So this one should be 6.9 power of 10 minus 4. So we will have the answer here is equal to 3.3 milliwatt.
3.3 milli.
Alright. So then the next exercise. So the question asks us to repeat the part B. So by using this equation. Right. So this is the equation of the Joule's law. Okay, if we apa nama tu? Dia punya persamaan asal. If we want to calculate the power by the respective of field. So that's why we have the field parameter here. So in order to solve this equation, so we need to derive first our expression for electric field. Okay. So the electric field can be expressed by using this equation. So we have the vector of E is equal to minus del dot V. Okay. So if we consider, so this is our copper wire. Okay. And then the copper wire is injected with certain voltage equal to 1.5 millivolt. Alright. So instead of so we know that from this point until this point, the potential is equal to 1.5 millivolt. So we need to express this potential in terms of function of Z. Okay. So because of we know that the total potential, okay, from this point to this point is equal to 1.5 millivolt. So and the potential is in terms of Z function. Okay, so Z function here. Okay, because we know that when we say we have a cylindrical coordinate system, or we have a cylindrical shape, so we have three basic components that exist in cylindrical coordinate system or coordinate shape. So we have R, so we have phi, and we have Z. So definitely we assume that so the potential different across this conductor is uniform. So that's mean that we didn't have any potential difference in terms of R direction and phi direction. So the potential difference is only exists in a Z component. So that's why I make this step. So we have in a 50 meter, so the potential difference is equal to 1.5 millivolt. Then if we want to express the potential difference in terms of length, alright, so we will have the volt is equal to 30 micro multiplied by Z. Okay. Then we put this expression of V inside the yang tadi lah, so minus vector of E is equal to minus del dot V. Alright, so kita ada yang ni lah. So because of the potential difference is only exists in the Z component, so we can abaikan ataupun neglect the other direction lah, r and phi direction. So that's why, so we will have the final equation for this expression is equal to E is equal to minus Z d over dz 30 micro. Okay, 30 micro Z lah. Okay, because of the length of this conductor is a function of the Z. Then if we perform this operation, then we will have the expression for the electric field intensity is equal to minus Z cap 30 micro volt. This one is volt per meter lah. So the unit of for the V for the E. Then so once we get this expression, so what should we do is just put all the parameter that we know inside this expression lah. Alright. So because of we are using cylindrical coordinate system, so the dV will be in r, dr, d phi, and dz function. So we need to perform volume integration. So it will be involved with the triple integration. So r is from 0 until 2 cm. Okay, so this one is represent the radius for the conductor. So phi is from 0 until 2 pi because we consider a full cylindrical shape, and the z, which is represent the length of the conductor, is from 0 until 50. So this is the sigma for the copper wire, and this is the expression for this one lah. Alright, so we have the amplitude for the E, vector of E, with the power of 2. Okay, so kalau yang ni pun basically kita boleh buat directly macam ni lah. Okay, so basically E, vector of E. Okay, so since this is the amplitude, so basically is equal to, the amplitude for this vector is equal to 30 micro kan. Okay, so multiply by 30 micro. Then if we solve this one, then we will have this expression lah. Okay, so kat sini ada 30 micro with the power of 2 time with the sigma. Alright, so because of in this function we didn't have any term of r, phi and z. So this is the solution for this triple integration. So we have r here, so integrate it, then we will have r squared divided by 2. So limit it from 0 until 0.02. Right, so the integration of 1 is equal to phi, okay, because we didn't have any phi expression. So the limit is from 0 until 2 pi, so according to this limit. And the z, because of we didn't have any term of z, so by solving the integration, we have z, the limit is from 0 until 50. So kalau selesaikan ni, then we have 3.3 millivolt. Okay, the same answer as we get by using the circuit analysis technique. Okay, so review for magnetostatic. So maybe some of you have been watched several video for the magnetostatic. Okay, so so this on this session, so I will try to explain about the what you should know in this topic. Okay, so similar like what we have been learned during electrostatic. So the magnetostatic, so the first thing that we should know is the source. Okay, source of the magnetic field. Because of we are concerned about magnetostatic, okay, and the magnetostatic is due to existence of magnetic field. All right. So the source of the magnetic field is a current. So basically, the current can be exist in either right. Okay. So the current can be exist either in form of AC or DC. And because of in this topic, so we are more focused. We are the focus that in this topic is about magnetostatic. So because of that, so we are more concerned about the DC lah, rather than AC. So the DC current will be produce a magnetostatic field, okay, or the static field. Okay. If we inject, if we the study is focused or given to the AC current, then in this particular case, so we will study about time varied field. Okay, so when we deal with magnetostatic, so basically the main equation that we will use is the third and fourth Maxwell equation. Okay, Maxwell equation. And because of we are dealing with a static field, so whatever parameter that involve with the time variation will become zero. Okay, so we will have del dot with a vector of b is equal to 0. So this one is the third Maxwell equation. And then we have another one is del cross with a vector of h is equal to vector of j. So this one is the fourth Maxwell equation. So based on this equation, so we will know that basically in a magnetic field, so the parameter that we need to that we will involve is first is the vector of B. So this one is a magnetic flux density, right? So the unit of it is Tesla, and then we have the vector of H, which is represent magnetic field intensity. So the unit of it is ampere per meter. Okay, so if we look into these parameters, so basically so we will have similar parameter, okay, in electric field. So for example, for the B is maybe related or maybe similar to what we have in a vector of D. So electric flux density, the unit of it is Coulomb per meter squared. And for the field intensity, so in electric field, in electric field perspective, so we have the vector of E. Alright, so the unit for the vector of E is volt per meter. Alright. So similar like similar like on what we have been learned in electrostatic. So in magnetostatic, so the main focus will be given on how to express our vector of B and the vector of H. Okay. So this vector can be derived by using several law. Okay. Similar like what we have in electrostatic. Okay. So first, so we can apply the law the law that we call as Biot-Savart law. Okay, Biot-Savart law. Okay. So we can also develop or derive the expression for the B or H. So by using Ampere law. Okay. Alright. So that's all the law that can we be used to derive or to express our expression or equation for the B or vector of H. Okay. In Biot-Savart law. So basically the expression for the H, okay, because normally we will start with the field intensity. Okay, similar like what we have in electrostatic. So we start with the expression for the E first, then from the vector of E, expression for E, then we derive what is the expression for the D. Okay, in Biot-Savart, so we will have the expression for the D. Okay, it start with the differential form of the equation. So we will have dH is equal to, so I divided by 4 pi. Okay, line integration. So dl cross with r cap divided by r squared. The unit is ampere per meter. Alright, as I mentioned just now, so basically we will have the source for our magnetic field is come from a current. Okay, okay, the source of it is come from current. So that's why we will have the expression of I here. And basically, so the current can be expressed by using absolute value. Okay, so similar like what we have in the charge. Okay, so we can express it by using absolute value. Okay, so the unit is ampere, and also we can represent the current in terms of density value. Okay, so the difference between density value of the current and density value of the charge. So density value for the current can be divided into two types. So first is surface. Okay, so this one will be represented by the vector of Js. The unit is ampere per meter squared. The current can also represent in terms of volume density. Okay, so normally the volume density will be represented by the symbol of a vector of J, and the unit is ampere per meter cubic. Okay. In a current, so we didn't have any line density. So because of the fact that our absolute value for the charge is already represent the line. Okay, so the line density. Okay, because so normally when we talk about current, okay, so basically we will consider a conductor. Okay, so they say we have a cylindrical shape of the conductor. Okay, and then basically uh, we consider the current that flow inside this conductor. Okay, so by referring into this setup, so we know that the absolute value for the current is already represent the line densities. Okay, if we compare with the charge perspective. Okay, so in current we cannot have one isolated current as we might have in a charge. Okay, so that's why the absolute value for the current itself in a line density. Okay, and the density value for the current can be expressed so either by using the surface, or by using the volume density. All right, so by referring to this fact, okay, so we need also the expression that represent our relationship between vector of H and the current in that density value. So therefore, if we have the current is represented by the surface density, so we will have H is equal to 1. Okay, so please don't get confused. So this is the current I, so this is 1, right? And surface integration of vector of Js cross with r cap, so divided by r squared, the unit is ampere per meter. And for the expression of H with the current being represent by its volume density is equal to dH is equal to 1, right? So this is 1, so divided by 4 pi. Okay, so volume integration of the vector of J cross with r cap, so divided by r squared ampere per meter. Alright, so the concept of the field basically is almost similar what we have in electric field. Okay, so let's say we have one conductor here. Okay, so one conductor, and inside this conductor, so we have a certain value of current flowing inside that conductor. Okay, so we will have current here. Okay, so depending on the direction of the current, so basically we will develop some electric fields around of this conductor. I think you might perform this experiment. Okay, so during your secondary school or during your matriculation. So how to prove that the existence of the field surround this conductor if we inject some value of the current inside that particular conductor. All right. So let's say in this case, so we will have uh, electric, sorry, magnetic field that induced around it in this direction. Okay. So we will have, okay, so if we refer to the right hand grabs rule, so in this side, so we will have the direction of field is flowing outside from our plane here, from our screen. And in this side, so we will have the direction for the magnetic field is flowing inside, okay, our screen. Okay. And so let's say we want to find, so what is the field, okay, so the value of field in this point, for example. Okay, so the P point here. So what we should do, okay, so similar like what we have in the uh, in an electrostatic. So basically we need to create a vector, okay, so potential vector here, or position vector here to represent the direction and distance between our source of magnetic field and our test point. All right, and then after that, how to find it? So basically we can use whatever equation that we have here, so by using Biot-Savart law. Right, so the detailed explanation you might see inside the video lah. So this one is um, only brief of of the concept of the how to derive the magnetic field. Okay, so the next law is what we call it as a uh, oh sorry. So we have another law here. Okay, so we have third law. Okay, as in electrostatic, so we have a Gauss law. So in magnetostatic as well, we have a similar law. Okay, so we call it as the Gauss law. Okay. So all this law will be provide information or technique on how to develop expression for our B vector B and vector H. Okay, and the second law that we learn in this topic, so we call it as a we call it as a Gauss law. So under this law, so we will use the basic expression. Okay, whereas we have on the third Maxwell equation, so we have del dot D is equal to 0. Okay, and basically this form can be interchanged between differential form and integration form. In integration form, so we will have a closed integration of surface D dot ds is equal to 0. Okay, and in order to convert this from differential to the integral form, so we are using divergence theorem. Okay, so the last law that we will learn in this in this topic, okay, so what we call it as a Ampere law. In this Ampere law, so we will refer to the fourth equation for the for the Maxwell equation, right? So we will have our del cross with H is equal to G. So this is the original equation as the state in Maxwell equation. Then the differential form for this Ampere law can be interchanged by using a Stokes theorem. Okay, and the solution of it will become a close integration of a contour of a line to h dot dl is equal to I. Okay, so the conversion will be used the Stokes theorem. Okay. Then if we go further, okay, during this topic later on, so we will see that another set of equation. So whereas we will have surface del cross with h dot ds is equal to surface integration of g dot ds. Okay. Then from this series of equations, so basically depending on the suitability of the problem, so we will use either one of these one of this law in order to derive our expression for the magnetic field component. All right. So in if you remember in electrostatic, so we learn about the topic what we call it as a potential. Okay, potential in a electric field. Okay. So whereas the potential of electric field is defined as so how much energy that we use in order to move a charge, okay, either positive or negative value from one point to another, okay, from point one to the point of two, okay, and the motion will be uh, involved in terms of variation of position and position and speed. Okay. So, however, in a magnetic field, okay, so in a magnetic field, the situation that we'll have, so we have already the charge motion, okay, from one point to another, okay, and then the due to this charge motion, we will have some value of the current, okay. So it is also stated, okay, in the concept of magnetic force. So magnetic force will not change the distance. No, sorry. The magnetic force will not change the speed. Okay, the speed. Okay, but the magnetic force will be only change in terms of direction for the charge motion. Okay, so this one is what you have been see in the first video for the magnetostatic. So because of this fact, okay, basically the potential inside our magnetic field is equal to zero. Okay, but in order to ensure the divergence of the magnetic flux density, okay, so the divergence for the magnetic flux density is given by this equation is equal to zero. Okay, so in order to prove this one, so basically we will introduce another vector. So we call it as a vector A, and this is what we call it as a imaginary of potential difference in magnetic field. Okay, so later on we will see how can we derive this vector. All right. So once we have been know, okay, the expression that represent our B and our H, So basically, we can apply this equation into to get the uh, some application in a magnetic field. So first, we can derive the force the force value, okay, in terms of magnetic force. Alright, so we can, based on the expression that we have here, so we can calculate in terms of the magnetic torque, okay, which is the force that cause any body to a body to rotate. Alright, so from that as well, so we will have, we can express, or we can calculate the value for inductance. Okay, so this is a storing element. Uh, okay, storing energy element in a perspective of magnetic field. And then from that as well, so we can find, so what is the magnetic energy. All right. So later on we will see the detail of it. Okay. Similar like what we have in electric field. Okay. In the magnetic field as well, we will deal with the material type. So the material can be classified as a ferromagnetic, paramagnetic, and diamagnetic. Okay. Some reference of books use the term of non-ferromagnetic to refer uh, non-ferromagnetic to refer diamagnetic material type, okay, inside a magnetic field. All right. So and this material having a constitutive parameters of mu. Right. So we have mu is equal to mu r dot mu naught. Okay. Or the mu naught is represent the air permeability. So this one is air permeability, and this one is represent relative permeability. Okay. So the value of mu r is depending on the which classification of this material. Okay. If the material is classified as diamagnetic, so basically the value of mu r will be equal to 1. Okay. If that particular material is fall under ferromagnetic type, so basically we will have the value for mu r is probably more than 1000 than 1000. All right. So in the material subchapter, so we will see one of the important characteristic, okay, of the ferromagnetic material. Okay, that particular characteristic is to measure the quality of the material, and the characteristic, so we call it as a BH curve. All right. So in BH curve, so basically how can we find the curve? All right. So let's say we have one ferromagnetic sample, okay, in a ring shape. So then, so we will make two coil. Okay. So this is the first coil. So this coil, so we call it as a excitation coil. excitation coil, and the second coil is the coil that we rename it as surge coil. So this is surge coil. So inside this excitation coil, so what will happen is, so basically we will inject some value of the current, okay, inside this coil, and then in the end, so this value of the current, so we will convert into the value of magnetic field intensity or the vector of H. Alright. At the same time, when we inject the current at the excitation coil, so basically, and then at the same time, we will measure the voltage across our surge coil here. So from the voltage that we have, so we will convert to the value of magnetic flux density, and then from this setup, so basically what we'll have, so we will have a graph like this. So this is B, so this is H. The unit of B is Tesla, and the unit of H is equal to ampere per meter. Okay, so normally we need to plot this graph in a kilo ampere per meter order. Okay, so basically what we have, uh, so when we initially inject the current at the excitation coil, okay, from the zero value, okay, until certain value of the current. At the same time, we are measuring the voltage here. So what we'll have is we have this kind of characteristic. Okay. So and then after that, what we will have to do is, so we need to decrease the value of current here. So from that previous maximum value to the zero value, and then we are trying measuring the voltage across the surge coil. Okay, so basically what will happen, instead of by using the same route, so basically the reduction of the value for the magnetic flux density will become this direct, this way. Okay, so this way until the current becomes zero, and then the current is still continuing reducing until the value of the current is become negative value. So we will have this loop. Okay. Then after that, from this maximum negative value here, so we'll increase back the value of the current to the positive value back. So we will have this curve. Okay. So this is what we call it as a BH curve. So on this BH curve, so we will have some information, some important information regarding this material. So first is what is the value of saturation value for the magnetic flux density. Alright, so this will be determine whether this material is good enough for certain application or not. And the second thing is, so what is the value of here? Okay. So the value of B when the H is equal to 0. And the third one, so hysteresis, this value. So what is the maximum of this curve? So this is our hysteresis. The larger the value for hysteresis, so that means it's represented the material is not, so it's not a good material, ferromagnetic material, because this hysteresis value will be contribute in term of, okay, then because of we have more than one type of material, okay, so definitely we need to consider about the boundary condition. So inside this boundary condition, so let's say we have one boundary here, and And then so we have, so let's say this is medium 2 and this one is medium 1. Alright. So on this particular case, so we will observe. So what will be happen to the value of the field when the field is travel from one medium to another. Okay, so this one we will have the vector of h 2 and this one will be the vector of h1. Alright. And because of we have two different mediums, so definitely, so we will have a different value in terms of mu value. So maybe mu r is equal to mu r2. So mu r is equal to mu r, sorry, this one supposed to mu r1. This one is equal to mu r2. Alright, so I guess that's all for the summary or for the magnetostatic topic. So for the detail in terms of each subtopic, so I will explain it in a video. Magnetostatic Coulomb's law. Okay, so in this law, so basically the focus that given in this law or either in the Gauss law, basically to uh, derive okay expression for vector of E and the vector of D. Okay, so the E is represent electric field intensity. Okay, so represent the strength of the sorry, the strength of the field. So the unit is volt per meter. Okay. So the unit is volt per meter, and then the D is represent electric flux density. Okay, so the unit of it is equal to Coulomb per meter square. Alright, so you need to differentiate the electric flux density and the surface charge. Surface charge density because it's carry the same unit, but actually those value is represent a different physical representation. Alright, so in order to derive the expression of E, okay, so since the electric field, the source of electric field is come from charge. Okay, so the charge can be represent either its absolute value. Okay, so the unit is Coulomb, or can be also represented by using density's value. So the unit of weight is depending on the type of densities. Right. So let's say we have a line density. So the unit is Coulomb per meter. If we have in a surface density, so the unit is Coulomb per meter with power of 2 or meter squared. And we have the charge is represented in a volume density. So we have the unit is equal to Coulomb per meter cubic. Alright. So let's consider the first case first. Okay. So let's say we are deal with the absolute value or most of the case basically we will represent it or mention it in a isolated particle charge. Okay, isolated particle charge. Okay, so let's say we have one charge and the charge is located in this position, for example. Okay, let's say we consider a positive charge. If we have a positive charge, basically the positive charge will be developed fields around it a direction of outward from its self. Okay, so this is our electric field. Okay, so let's say we want to find, so what is the value or the expression that represent our electric field intensity in this case. So let's say by referring to this point, for example, our P point. So we need to find what is the E at this point. So in order to derive expression, okay, for that particular case, so we need to first develop the vector R. So this is the vector of R. So this vector R is represent the direction and distance between our charge and our test point. Okay. So one technique that we can use in order to derive our E expression is by using the Coulomb's law. In the Coulomb's law, said that uh, the electric field intensity, okay, so produced by any charge at a certain position can be calculated by using this expression. So we have R cap, so Q divided by 4 pi epsilon R squared. The unit is volt per meter. Okay. Basically, from this expression, okay, so since we have this is the unit vector, and the unit vector can be expand into the other expression. So let's say we have, so the unit vector of R is equal to vector of R divided by its amplitude. All right. So by considering this expression for the R cap or unit vector, so if we put the expression inside this formula, so we will have Q divided by 4 pi epsilon, so multiply by the vector of R, so divided by R with the power of 3. Okay, so this is the first statement for the Coulomb's law. And the second statement for the Coulomb's law. So let's say in this case, so we put another charge, okay, inside the electric field that produced by the other charge. So let's say we put another charge here. So this is Q prime. So because of we put another charge in the presence of electric field, so that particular charge will be experience some force. Okay, so because of the polarity is the same, so basically we will have generate some ripple force here. So this is Fe. So Fe in a direction of repel to each other. Okay. So in order to calculate the force that experienced by this particular charge, so we have expression that Fe is equal to E multiplied by Q prime. Okay, and the unit of it is equal to Newton. Alright. So this is the expression of electric field by considering if we have a single particle charge or isolated particle charge. So what will be if we have the charge in the line density, for example? Okay. If we have the charge is represented by the line density, so we can find the total charge is equal to line integration of rho L dot dl. So because of that, so the expression for E will be changed into 1, so divided by 4 pi epsilon. Okay, so multiply by vector of R divided by, or we can, let's say we are using the standard form as how we go, how we write that particular equation. So line integration of unit vector R to rho L, so divided by R squared dr. Okay, so again, so as we can see here, so we have expression for r cap here. So in the end, so we can change this r cap is equal to vector r divided by r, and then if we put this expression inside the expression, then we will have a slightly different shape of the equation. And if the charge is represented by a surface density, for example, in next case, so we have a surface density. So in this case, so we can find the total charge is equal to surface integration of rho s dot ds. So because of that, the expression for the vector of E will be equal to 1 divided by 4 pi epsilon surface integration, so r cap rho s ds, so divided by r squared. And let's say we have now the charge is being represented by its volume density. In a volume density in this case. Alright, so since if we have if we have the charge is being represented by the volume density, so we will have Q is equal to volume density rho v dot dv. Okay, and then we the expression for the electric field intensity can be write as this one. E is equal to 1 divided by 4 pi epsilon. So, volume integration. So r cap, which is the unit vector. So rho v dot dv. So divided by r squared. So the unit of it is volt per meter. Right. So similar like this case. Volt per meter. And then this one is also volt per meter. Okay. So let's see one how can we solve how can we solve the problem of derivation of electric field equation, so by using Coulomb's law. All right, so let's say we have one charge here. Okay, the positive charge. If we have a positive charge, so basically we will the charge will be induce an electric field, okay, in this direction outward from itself. Okay, and we need to find the value or the expression that represent the electric field intensity in this point, for example. So we need to find E at T. Okay, so in this case, so let's say we have the uh, the coordinate that represented by this point is equal to, let's say, x1, sorry, x2, x1. We just pick x, y, and z. Okay, so we assume that so this charge is placed in the origin. Okay, so let's say the charge is placed on origin. So the first step, so what we should do is, so we need to find the vector of represent the distance and direction, okay, between our charge and the test point. So equal to r, r vector of r. Okay. So as we already know, so the expression for the electric field intensity is equal to r cap, okay, q, so divided by 4 pi epsilon r squared, okay, volt per meter. Okay, so first we need to develop the expression for this vector. So the vector of R can be derived as follows. Because of the vector of R is travel from origin to the coordinate of x, y, z. Okay. So the vector of R can be represented as this one. So x cap x plus y cap y plus z cap z. Okay. And then the amplitude for it is equal to x squared plus y squared plus z squared and square root of it. So based on this expression, so basically, so we will have the expression for the that represent our E is equal to, so R cap is equal to vector of R divided by R. Okay, so we will have x cap x plus y cap y plus z cap z. Alright, so divided by its amplitude, x squared plus y squared plus z squared. Okay, so multiply by q, so divided by 4 pi epsilon and multiply by 1 divided by, so this is with the power of 2. So we will have like this one, y squared plus z squared with the power of 2 here. The solution of this one will be as a follow, 4 pi epsilon. Okay, so multiply by the vector of r here. So this one x cap x plus y cap y plus z cap z. Okay, so divided by its amplitude, x squared plus y squared plus z squared. Okay, so because of this is we have the power of half, and this is the power of 2. So because of that, the total the result for this expression will become the power of 3 divided by 2, and the unit is volt per meter. Then if we know the value for each parameter, so basically we can replace the symbol with the value, then we will have the absolute value for that particular field. All right. So that's all for the Coulomb's law actually. Gauss law. So in this Gauss law, so basically the expression for the Gauss law is start from del dot with d is equal to rho v. So this one is based on the Maxwell equation. Okay. From this Maxwell equation, so basically with a certain step of derivation, so we will have the first one is del dot d dot dv is equal to, this one is volume integration. So volume integration rho v dot dv. Okay, and then this solution as well will be equal to closed surface integration d dot ds, and the result of it is equal to q. Alright, so in this Gauss law, so what we expect to know, alright, so let's say we have one particle charge. Okay, so one isolated particle charge, so positive q for example. Alright, so in order to relate with the Coulomb's law. So if we have a positive charge, so basically we will have the field will be flowing outside, okay, from this particular charge. And based on this fact, so basically, so we will have the shape of this field in a spherical shape. Okay, so like this. Okay, so because of the shape of the charge as well in a spherical shape. Okay. So in this case, so we need to find the expression for the E. Okay, so the difference between Coulomb's law and Gauss law. So the expression that we going to derive is based on the certain area. Okay, so this, let's say this is our area. Okay, then we need to find instead of D, okay, because of the Gauss law, we will deal more with the flux, so we will have the vector of D here. But eventually, so we can change, or we can express the value of electric field intensity by using the vector of D, or the vector for the electric flux density, whereas the vector of D is equal to epsilon multiplied by the vector of E. Alright, so in this case, so how can we express our vector of D? So let's say we have, this is our charge, and this is the shape for the field intensity, or the electric field. So basically in this case, so we can apply any of equation or term that we have here. Alright, so but in this case, so the most convenient term that we need to use in order to solve it is by using this equation of Gauss law. So Es is equal to Q. Okay, so in some case, so the value of Q can be directly given. Okay, so let's say in this case, so let's say because of the charge is exists in a particular charge, so we will have the value of Q in terms of its absolute value. Then, so from this expression, so because of the shape of our field in a spherical shape, so we will have our vector of D is equal to r cap dr. Right? So this is by referring that our shape of the electric field is in spherical shape. Okay, so that's why we are using component of spherical coordinate system in this case. Then later on we can find out whatever uh, based on this argument or this equation. So let's say in order to solve this one, so in order to perform a closed integration of surface, so we need to integrate this surface against all surface that exist. Okay, so because of we consider the shape of the electric field in a spherical shape, so therefore, so the total surface is equal to 1, right? So that's why in this case, so we will have the solution for this closed integration will be equal to double integration, so D, the vector of D, so this time the vector of D can be expressed by using its general form is equal to r cap dr. Okay, and the expression for the vector of ds will be also in a r cap direction. So in a spherical coordinate system, so we have r cap, r sine theta, d theta, d phi. Okay, and because of that, so we have limit the theta is from 0 until pi, and we have phi, the limit for phi is from 0 until to pi. Okay, so the solution of this one will be equal to Q. So this is if we are referring our shape of field in a spherical shape. Okay, so let's say we have our charge instead of by represent by its absolute atau isolated particle charge. So let's say in this case the charge is represented by its rho L. Okay, so line charge density. So whenever we have the charge density in this shape, okay, so we assume that basically most of the case when we have rho L, or the line is represented by the charge by the line density. The charge is being represented by the line density. So we will have the shape of the electric field in a cylindrical shape like this one. Okay. So let's say the field will be developed in this direction. Sorry, this is D. So we start with D. So this is D. Okay, and because of the electric flux density is indeed in r direction. Okay, because if we consider in a cylindrical coordinate system, so we have r, phi, and z component. Okay, so let's say we have the vector of D is equal to r cap dr. Okay, so which is the representative of electric flux density that exists in the r cap direction. Okay, so in order to solve this, so we can apply the same equation. So the closed integration of surface, so d dot ds is equal to q. Alright. So in this case, the value for the charge is represented by its line density. So therefore, so we can divide this solution into two different parts. So first we need to find what is the general expression for the Q. So Q is equal to line integration of rho L dot dl. Okay. So since in this case the line charge density is exists in the z cap direction, so we will have integration of z from this 0 until z, okay, certain value of z. So rho L and dl will be in dz. And the solution of this will be the solution of this expression or mathematical operation will become rho L multiplied by z. Okay. Then so we need to solve this side of equation, this side of an equation. All right. So in order to solve this one, the closed integration of surface vector d dot ds. Okay. So because of in this case we are dealing with the cylindrical shape. So in a cylindrical shape, so we have three different area. Okay, so first we have on the top side. So this is the top surface. Okay, and then we have the second surface is on the bottom one. So this is on the bottom surface. Okay. And we have another surface in the direction of the side. Okay, so this one on side. All right. So, but at the same time, so the flux or the electric flux density is only exists on the r cap direction. All right. So in order to solve it, so let's we derive one by one. So they say in this case, so because of we deal with the surface integration, then we need to perform double integration. So the vector of d is equal to r cap dr. Okay, so let's consider on the top surface first. On the top surface, the area is in z cap direction. So that's why in this case, so the vector of the s is represented by z cap. Alright, so the parameter will be changed is in terms of r and d phi. So we have r d phi dr. Right, so the limit phi is from 0 until 2 pi because we consider the full structure of a cylinder, and the r will be differed from 0. The limit of r is from 0 until r. Alright, so this is one for the top surface. Okay, so because of we have closed integration of surface, so we need to consider all the surface. All right, and then so we need to add with the surface integration by considering the bottom side. So the bottom side, the direction of this side, this surface in minus z direction. So we will have still have double integration. So the expression for the electric flux will be r cap dr, and the ds will be in minus z direction. So r d phi dr. Right, so the limit is the same limit as previous one. So phi 0 until 2 pi, and we have r from 0 until r. And then, so we need to consider as well on the side surface. On the side surface, so we need to perform a double integration as well. So the expression for the electric flux density is equal to r dr. Okay, and because of on the side surface, the direction of the ds will be in r cap direction. So therefore, so we will have the expression for the vector of ds is equal to r cap d sorry uh, all right, so r d theta and dz. Okay, so by referring into this expression, so we can see that okay, so this expression will become 0, okay, because in the dot product, so r cap dot with z cap will be result 0. So similar like this expression, so we will have 0 as well because of the dot product operation here involve the two with the two different components, so r cap and minus z cap. Then it will left us with this expression, okay. So I forgot to put the limit here. So they say the limit here is uh, this one is theta from 0 until 2 pi, and we have z is from 0 until z. Alright, so the solution for this equation then we will have is equal to dr dot with r. So r is the radius. So the if the question give the value for r, so basically we can put directly the value of it. Alright, so the theta is from 2 pi until 0, so 2 pi, and the z is equal to z. So we will have dr r 2 pi multiplied by z. So this is the expression or the solution for this equation. So, so finally, so what we should do is, okay, so because of we have the close integration of surface vector of d dot ds is equal to q, then we will have dr dot r 2 pi z is equal to rho l z. Then we will have the solution for dr is equal to rho l, so divided by 2 pi r. Okay, so this is the example or the example of the question on how can we apply Gauss law, okay, in order to solve any electromagnetic problem. And basically is how on it depend on how the question want to how what is the question want you to solve it, right? So based on the step of the dedicated law, so basically you need to perform it step by step in order to solve any problem that given in the test, in the final, so on and so forth.